Hey, I got to show you something. Uh, Dr. Pickelstein here, and a friend of mine. He was also one of my professors at the Medical College of Wisconsin. He went off and began work at the Milwaukee School of Engineering. His name is Tim Herman, and the cool thing about this is he uh, he is now the director for the Center for Biomolecular Modeling. And so they come up with ways to help describe molecular interactions that can occur, and things that actually, when I teach general chemistry, for instance, things that I have to try to describe. And it's always hard to describe things like a molecule and things like that because the molecules themselves are invisible to us, and so we need models. And so this is a really nifty little model set. What I'm showing you here is water. This red is an oxygen, and the whites are the atoms representing hydrogens. So two H's, one O, H2O, that's water. So we have water here. Now, water is a very nifty little molecule. It has electrons associated with the atoms, but there are a lot more electrons that are associated with the oxygen than with the hydrogens. And electrons have a negative charge to them. So what that means is that these electrons build up on one side of the molecule, and there's not as many on the other side where the hydrogens are because they don't have many electrons. So essentially, there's something called a dipole that goes in that direction, the direction of my finger, where you have a negative, partial negative charge on one side and a partial positive charge on the other side. And what that does is it kind of sets it up to sort of, we can, it's not a magnet, but we can kind of use magnets to kind of see how they behave. So just like a magnet, let's see, I think I even have I have a bunch of magnets right here. When magnets are put together so that the north and south poles are together, then they stick together because opposite poles attract in the magnetic field. But if I'll flip this around, so now we have, look at that, it's not magic, it's just that I have a repulsive, there's some repulsion happening here because I put two north poles together. Actually, I don't know if they're north poles or south poles, but we have two like poles together. So much like how magnets behave, sometimes we can get these dipoles, these molecules that are polar, to behave something like a magnet. Instead of having a north and south pole, they have a negative and a positive end. So this is partial negative, that's partial positive, and just like charges, like poles repel, like charges repel, and just like opposite poles attract, opposite charges attract. Well, that sets up an interesting way in which these different molecules, if I have two water molecules, for instance, if I try to connect them so that they come together, what you can, I don't know if you can see this, but as I bring them together, they start to repel each other. And notice what happens when I kind of loosen this up. This is the negative side, this is the positive side. When I kind of bring these together, I dropped them. When I kind of force the two negative sides together, it turns out in these model kits there's magnets. And so it's set up so that the magnets represent the repulsive force that occurs. See, I can't get those together. It's fighting me right now. Oh! But if I just let it go, but look, it likes to stick to the positive end. So just like with a magnet, where the north and south pole attract, with a dipole, we have the negative, and that clucking is me getting a text. Sorry about that. So anyway, so that now I put those together and they stick together, and even though these are magnets that are built in to represent the electrostatic interactions, that's what we call the interactions between positive and negative charged items, components, atoms, portions of a molecule. So we can get those to stick together, and this represents what we call a dipole-dipole interaction. And it's a special type called a hydrogen bond, because a hydrogen is bonded to this oxygen in water. So that turns out to be kind of a nifty thing, and so these models are awesome for demonstrating the different dipoles and dipole interactions. So now I'm stringing the waters together, and they are interacting much like a magnet. Now, if like I said, so the one thing you won't find is they will not, see, I can force it, but it doesn't want to do that, it wants to do that. So the negative sides, negatives repel negatives, and that's exactly what I'm seeing here. But the positives stick really well. Now, maybe you have no idea what that is. Well, it turns out that this represents sodium chloride, table salt. And when table salt gets dissolved in water, it dissociates into what we call ions. This is a sodium ion, this is a chloride ion. Sodium ions have a positive charge. Chloride ions have a negative charge, and you can see there's little magnets here again. And that's going to help us figure out how to interact with water. So when these things dissolve, they dissolve in a very specific way. Negatives do not like to be together, and so this is a negative chloride ion, and when it comes to the negative sort of end, the more negative, the end of the water molecule with more of a negative character, they repel each other. See? Ooh, it doesn't like that. However, when the water molecule is oriented so that its positive end is near the negative, it sticks. And so what happens is as the waters interact with the chloride ion, you can see that they wind up forming what we call a sphere of hydration. The water molecules surround the ion and form a network of waters. And then what makes it interesting is now other water molecules come in, and they can interact with the water molecules that are in interaction with the ion dipole interaction that we see here with chloride ion, and now they can hydrogen bond and continue that hydrogen bond and dipole interaction network and build a big sphere. See how that everything's just clicking together, and you get this big sphere of hydration. Now you can do the same kind of thing with the sodium ion that we had. The sodium ion gets dissolved in water too, and just like before, the positive end of the water doesn't want to stick. It pushing away. There's a repulsive force, and so the positives repel each other. However, the negative sticks. So we can do the same thing, it's just that now instead of the positive end orienting with the ion, the negative end is orienting with the ion. And I say negative, it's not a formal negative charge on water, it's what we call partial negative charge. It's how the dipole is set up. There's more electrons, more negatively charged electrons on one side. So now the water packs around these ions. And again, we get the same kind of deal again. These things start forming their networks, and they start interacting, and they can form little balls and shells of water around it. So I love this little kit. It's called the 3D Water Kit, and I'm trying to figure out how to purchase it. This was sent to me from my friend and former professor, and I'm just really excited about this, and I thought I would make a quick little video to demonstrate how cool they are. You can do a lot of learning by playing with these things.